Our next measure of dispersion is called the standard deviation. It's quite a difficult calculation to make. What I have written up here is not really a definition, it's really just my own description of what I would say a standard deviation is. It's kind of hard to give a particular definition to it other than the calculation, which we're going to come to in a few minutes. So what I have up here, basically the idea of a standard deviation is it's the average distance. I'm putting that in quotes because it's not really the average distance, but it's kind of meant to be that way. The average distance from each data item to the mean of the data, okay? So if you were to calculate the mean, okay, that gives you kind of your central location within the data. And then what we're looking at with the standard deviation is how much does each individual data item differ from the mean? How far away from the mean is it? And then kind of take some sort of an average of all those differences or distances, okay? And that'll give you some idea of how spread out the data is from that central value of the mean, all right? So that's kind of the idea behind this. So the formula for it is here, and this is a confusing looking formula. I'll try to break it down and give you a shortcut to be able to, or a quick algorithm maybe, not a shortcut, to be able to calculate this thing because it can be tedious. And with larger data sets, this is very tedious and time consuming, and we have Microsoft Excel and other technology software to be able to do this on very large data sets. So the idea here, I've got some definitions of variables. X is a particular data item. So each of the values, I'm going to go ahead and use the age of Noah's ancestors as my example here, just so I have these numbers, I already have them up. So I have each of these values would be considered an X. It's a data item or data value, okay? Well, it's a data item, yeah. X bar is the mean. We've seen that notation before. We have to calculate the mean in order to calculate the standard deviation because the mean is part of this whole thing, right? I mean, it is the average distance from the data item to the mean. So we gotta know that mean, all right? N is the number of data items, which in our case here is gonna be 9, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, yep. And then S is our standard deviation, okay? So the first thing we need to do is calculate the mean, X bar. And the mean, remember this sigma notation, that zigzaggy type of thing, is a Greek letter sigma, and it stands for the sum of whatever follows it, the sum of the x's. So the sum of the x's in this case is just adding up all these values. So if I were to add those up, I should probably draw that a little bit nicer. There we go. If we were to add those up, maybe I should have done this ahead of time too, but I didn't. So it's 930, 912, 905, 910, 895, 962, 365, 969, and 777. And that is a grand total of 7,625. Okay, so that is our sum. That's the sum of x. So I'm going to put that in here. 7625, and of course I'm going to divide that by 9 because 9 is the number of data items we just looked at. Divide by 9, and that's a 847.2. It's a 2 repeated, which means it's 2 9ths. So I'm just going to approximate that. We'll just call it 847. I'm going to round it to the whole number. It's going to be close enough for what we're going to do here. Okay. All right, so there's our mean. So that means out of all 9 of these people, they live to be approximately at an average of 847 years old. Okay. So now the next part of the calculation, well, actually, that is all for the mean. So now we jump to the calculation of the standard deviation. And the standard deviation requires quite a bit of things. The first thing we have to do is we have to take that mean and we have to find the difference, or the distance I should say, the distance to each individual x value, each data item value, okay? So we're gonna look at how far each of these 9 values is from the mean. To do that, you subtract, right? That's why we have the subtraction. So it's x minus x bar, that gives you that distance. Now that distance could be negative and it could be positive, okay? We'll talk about that in just a minute. But it's gonna depend upon whether the x value is above the mean or below the mean. So if it's positive, the x value would be above. If it's negative, the x value would be below. All right, so x minus x bar. So what I'm gonna do is I'm gonna type in each of these 9 values, and at each one I'm gonna subtract 847, all right? So I have 930 minus 847 is gonna be 83. So right there is 83, right? That's 930 minus 847, all right? And what we're gonna do is do that for every item, all 9 of them. Okay, this does, like I said, this gets to be tedious, but it is an essential part of the calculation. 905 minus 847 is 58. 910 minus 847 is 63. 895 minus 847 is 48. 962 minus 847 is 115. All right, and then 365 minus 847 is negative 482. There's our outlier. In fact, it's the only one so far that's even below the mean. Everything else is above the mean. 969 minus 847 is 122. And then 777 minus 847 is negative 70. Okay, so there's only 2 values below the mean. Those 2 values are so far below the mean, however, that they really shift the mean over. They kind of skew things, skew that mean away from the rest of the data, actually. Kind of interesting. Okay, so those are the differences then. So then what we do is, when we add these together, we really don't want the negatives to cancel out with the positives. We want them all to build up because we're looking at the distance, not just the difference. And so we square these things to get rid of the negative. Now you might say, why not take the absolute value? There's reasons for that I'm not going to really get into right now, advanced statistics stuff. But in fact, I don't even remember all the reasons. But what we're going to do is square, and I know squaring does get rid of the negatives. We end up taking a square root later on, but we have to divide first. There's a lot of stuff going on here. So anyway, the next step, you do the x minus x bar, then you square all of those. So we'll do that. So now this is going to get really big. We do 83 squared. And this is where having an Excel spreadsheet is very nice, but we don't have that luxury to be able to do that right now. So 6889. Then I do 65 squared is 4225. 58 squared. And of course, the examples you guys have when you're doing your homework, or if I give you a test, you're not going to have numbers quite this big, okay? Things are going to be a little bit smaller, nicer to work with. In fact, maybe in the next video I'll do one that is a little bit nicer in terms of doing the calculations. 48 squared is 2304. 115 squared, 13,224. Now, here's our big one. Now, 482, negative 482 squared is the same as 482 squared, because when you square the negative, you get a positive anyway. And that is 232,324. So that's quite the number there. 122 squared is 14884, 14,000. Let's see, and then 70 squared is 49. Well, I know that one. Geez, 4,900. Okay, so those are our squares. Now, once we've calculated the difference and then squared each of them, we add them all together. That's what the sigma notation means. So I'm going to go right down this line and add all those 9 numbers together, and I'm going to get a sum. Okay. So that means, let's see, I gotta run through these. That number plus 4, 2, I'm gonna go from the bottom up. 2, 3, 2, 3, 2, 4, right? 2, 3, 2, 3, 2, 4. Making sure, and you can double check me on these if you really care to, because there's always the chance that I mistype something as I do this. 3364, 4225, 6889. Alright, hopefully I typed all that in because I'm not double checking it. I get, that can't be right. How can that be? Maybe it is right. Is that right? I got 286,000. 083. 286,083. That makes sense. So you got 32,000. Add in a 14, 15. That's 37. That's 60. And then the rest. Yeah, okay. I guess that makes sense. This is probably pretty close. All right, we'll go with that. So 286,083. So that's my sum. So now I can go over to my formula and plug that in and kind of work through the rest of this. So let me show you how that's going to play out. We'll start it up here. So S equals that thing. So it's going to be the square root. And then I put in, I already have the sum calculated. So this number at the bottom of the table goes in the numerator of what's under the radical there, the root. So that's 286,083. And then what I want to do is get the n minus 1 figured out. Okay, so n we know is 9. We've already calculated that. And, right, that's this value, it's the number of data items. And n minus 1 would have to be 8. Right, you just subtract 1 off. Again, there are reasons why we subtract 1 off. I believe that's called the degree of freedom. And again, there's statistical reasons for that, but I won't get into those. So you have n minus 1, which is 8 on the bottom. Now we got to do that calculation. So it is 286,083 divided by 8. Okay, so S then is the square root of, that's going to be 35,760. I'll just leave it at that. It's 0.375, so it's another 3/8. But I'm rounding a lot. I'm doing some major rounding on some of this stuff, so that's going to be good enough. And then I'll take the square root of that. Actually, on my calculator, I didn't round. I'm leaving that value in there when I do the square root. So it's really around 189. So the standard deviation is, I should really put an approximation here, approximately 189 years. Okay, so that gives us a measure of how spread out the data is from the center, from the mean, all right, on an average. Now that it's not really an average. When I say an average, I'm being very imprecise with that word, I guess maybe. Really the idea there is when we look at a standard deviation, we'll talk about this later on in the course. When you look at a standard deviation, it gives you sort of a measure of how much of the data is within 189 years of the mean. Okay, so we'll be able to take a look at that later on. But for right now, we're just trying to get the calculation down. So what does that mean? We'll talk about what it means another time. Really, 189 is the standard deviation. It gives you a measure of the spread of the data.